Okay, this lesson is how to do a basic, what we call scalar, or in other words, dot product with vectors. There's basically two ways you could multiply or get the product of vectors. This is one of the two, and I guess typically the easier and more understandable of the two. And the reason why we call it the dot product also is because it's notated through A dot B, whereas there'll be a different notation for the second type of product we go over later. The scalar product formula is A dot B, the vectors, equal to the magnitudes of AB times the cosine of the angle, in this case phi, between the two. Now, we're only going over the general process, and this example doesn't apply to any real situation. It's just any two random vectors. But in the future, one place we will use this is when we get to a topic called work. And I may refer to that just a little bit to give you a better understanding of why in the world we would need this for any reason. But let's first look at this diagram. Notice it's not head to tail because we only use head to tail for addition of vectors. So we have two vectors, in this case vector A and vector B, of two quantities with an angle phi in between them. And I listed just some numbers to use as an example for the magnitudes of vector A, B, and the angle phi between them. Now, first, it's pretty simple to use it straight up. It's popping in just the magnitudes necessary. So I would take the magnitude of vector A, 42.1 newtons, multiplied times the magnitude of B, which is 30.6 newtons, times the cosine of the angle in between, so that would be the cosine 30. And we run those numbers in our calculator, which I haven't done yet, so I'll do right now. So making sure our calculator's in degrees, that's pretty important. Times 42.1, and the scalar product or dot product, otherwise known of these values, are going to be equal to about, let's say, we'll use proper sig figs here, so we should have 3 total, so it should be about 1,120, and if those were in newtons, our scalar product, well, if they were both in newtons, we're not going to really actually worry about the units for now. I'm going to change something. Oh, I'm going to make this unit a meter to better illustrate an example I'm going to get to in a moment. So I'm going to change that from a force vector to a displacement vector. So that way our answers would be Newton meters. That's going to be an actual one we'll use later. Now, what does this mean is the more important thing. It's simple to run the numbers through that formula, but the meaning is what really matters here. And here's what we actually did by throwing in this cosine phi of the angle in between the two. We basically, the cosine isolates the x component of whatever way you want to look at it, either of the two vectors. So let's look at the b vector b, which is right beside it. By putting cosine theta beside it, that isolates the x components, which we could draw right here. We could highlight it right now and think of that, so I'll kind of draw over it. The x component of vector b, as we did in the component methods earlier, would be that one right there. Now, why do we want to isolate that one? Because the scalar or dot product only wants us to multiply one vector times the piece or component of the other vector that is in the same direction as it. So while vector b does have a y component right here, the y component is not in the same direction as vector a. Therefore, it's irrelevant in the scalar product. What this does is just isolate a component of one times the full piece of the other and gives us a value for that. Now, why might we really do this is the more important thing. A good example is when we get to forces and displacements in a section we call work and energy. And when you're pulling a wagon, let's say, let's pretend vector B is the pull of a wagon in newtons, so it's a force, and vector A is the displacement in meters that we're pulling it. Well, the work you do, it turns out, is only done on the axis you move on. So if I'm pulling on a wagon, yes, I'm pulling up on it, but if it's not moving upward, it really has no effect on the energy I'm using or the work I'm doing on the object. Now, we'll expand on that much more later, but that's a real application of this. So finding the scalar product is pretty simple. Knowing what it means is even more so important. And one other thing worth noting is it is a scalar product, so it should not have any true directional meaning. But here's another confusing thing. Scalar products can be positive or negative, but we got to be careful because those positives or negatives on a scalar product don't really represent a direction. They simply would represent a net amount. So a lot of scalar products are used, as I said, for work and energy. Work and energy do not have direction, but they could have net positive gains or negative losses. So if we do have a plus or minus on a scalar product, it's simply due to it being a net gain or loss, not a direction like north, south, east, or west, or anything like that. This is going to be very important to note whenever we apply this in sections here and beyond.